story on the following problem. Okay, how to measure entanglement in many-body atomic systems. Okay, and let me start by acknowledging my co-workers for the first part of the talk. This will be mostly work done with Benoît Fermersch and Peter Zoller in Innsbruck. And for the second part, this is work done with Pasquale Calabrese, Giuliano Giudici, Tiago Mendes Santos, and Jack Turkeshi in Trieste. So why are we interested at all in studying, either experimentally or theoretically, entanglement in many-body systems? I think, at least from my viewpoint, there are three reasons. The first one is the entanglement is a resource for quantum information tasks. So, like, for instance, quantum communication, so on and so forth. So it would be nice if we can quantify or measure it in concrete experimental systems. The second point, which has been, I think, partly overlooked, underlooked so far, is that entanglement can serve us as for certifying certain classes of quantum simulators, and also, and this instead is very well known, to quantify complexity. This is something which, for instance, people working in tensor networks are very well aware of. The third motivation, which from my viewpoint is the most important one, comes from many-body theory, either in high-energy physics or in condensed matter, is that entanglement is actually fundamental to characterize, and in some cases even distinguish, quantum states of matter. This was partly already introduced yesterday by Hans Peter when he did discuss topological order. It's a kind of order where entanglement is key. You cannot distinguish it by means of conventional local measurements or local concepts, like spontaneous symmetry breaking. But there are also other classes, like, for instance, quantum criticality, where entanglement provides a different perspective on a problem with respect to conventional diagnostics. Okay. So now let me start with a provocative slide. Where we are in terms of measuring entanglement in many-body systems. And let me emphasize that this is about measuring. Measures is not about witnesses. In witnesses, there are definitely, the view is much more optimistic than the one here, also thanks to theoretical work done by many people, including our chairman here, for instance, in the context of Fisher information. So here, in this axis, I plot the complexity of correlations. Let me say the number of spins of a certain subsystem whose entanglement we can measure with respect to the rest of the system. Okay? And for one spin, a lot of work has been done in experiments. And this is typically done through tomography. Okay? So through full resolution of the reduced density matrix. Now, if you want to go the next step of order 3 to 4 spins, we know now that there are ways of doing that through Oong-Mandel interferometry. It's actually not measuring entanglement, but measuring Rayleigh entropies, which are related. And this was work done, this is an example taken from a paper by Marcus Greiner group. And these are the theory proposals discussing this. And the idea is that in these systems, you can measure, for instance, powers of the reduced density matrix. These are very complex experiments because you need 2 copies of the very same reduced density matrix, and you have to let them interfere, so in principle you have apply an n-body gate operation. Okay? It's very remarkable that this actually has been done at these system sizes. Now, if you want to go to the next step, I think the largest system size where people have measured entanglement so far is trapped ions, by far. Okay? It's almost 1 order of magnitude. This is a recent experiment done in a group of Christian Roos and Rainer Blatt. And the idea there is instead of having conventional copies, you actually interfere a system with itself through virtual copies. I will actually have a slide discussing this so far. But you see, these numbers, these are very small. Okay? The idea is that if you want to really measure entanglement in many-body scale, like 10,000, thousands, okay, we probably have to try to look at different paradigms to do that. Okay? And this is what I want to show you today. Okay? And the message in a nutshell will be the following, is that there are scalable schemes to measure entanglement, particular entanglement spectra, in experiments. This requires us to have a detour, which will be very short, on the theoretical description of what is called entanglement thermodynamics, okay, or entanglement spectroscopy. And then, at the end, I show you that beyond entanglement spectra, actually, one can measure entanglement entropies, entanglement capacities in many-body systems. And I will give you some concrete examples now. So these are 3 examples that I will be discussing. The first one is measurement of Ising type chains of entanglement spectra, for instance, detecting a quantum phase transition by looking at the closure of the Schmidt gap, okay, the entanglement gap, as a function of the parameters. So these are measurements of what is called central charge, which is an important quantity in characterizing quantum critical points in one dimension. And they are motivated by recent experiments in Harvard, in Rydberg systems, in the lab of Misha Lukin. And these are discussed through entanglement capacity. Okay? And these allow us, with reasonable system size like 20 to 30 spins, to detect almost unambiguously signatures of quantum criticality. And this is instead something different, is a measurement of the von Neumann entropy as a thermal entropy for two-dimensional spin models. And what I want to emphasize here is that this kind of, these numerical experiments that we showed how it works, they are done on very small system sizes, but these are done on large system sizes, okay? And the method that I will be discussing you within some constraints allow us to probe entanglement really at the large scale of highly non-trivial many-body systems. Okay, well, where is the catch? I mean, where is the trick? Okay, there must be a trick, because it's clear that you cannot measure entanglement for an arbitrary many-body state because you will have to do tomography at some level. Okay, so whatever I'm telling you either is cheating or has to work under certain assumptions. Well, it does indeed work under certain assumptions. This kiss of death. Okay, this is the disclaimer, and what I will be telling you works for ground state systems where there is an approximate relativistic invariance. Okay, this is a very strong word. Okay. But it's actually something simple. It's essentially telling us that this works if you have spectra, which are linear as a function of momentum, or if they have massive. Okay? What is this discussion about? Well, luckily enough, most phases, well, essentially all phenomena in energy physics and most phenomena in condensed matter are in this class, but not all of them. For instance, ferromagnetism, we know that is typically described by dispersion relations which are quadratic, and whatever I will be telling you about will not work for ferromagnetism, or shall not work. Actually, in some cases it works, but we don't understand why. Okay? So there is this restriction that I will be discussing later on in more detail. Okay. So this is kind of the outline. Okay, first I will give you some few additional motivations. I will define the grand challenge and then tell you a bit of our results. Depending on time, this last part can be a bit sketchy. Okay? So let us define entanglement as follows. I mean, we have a physical system that we bipartite, so there are two parts, A and B. And the Hamiltonian is typically written as a sum of the terms acting on A, the terms acting on B, and the terms acting on the boundary. And what we are interested in, if we are interested in entanglement, is actually the reduced density matrix, which is obtained by tracing over part of a system, like, for instance, say, psi, a given vector that for us will most of the time be the ground state. So, and this reduced density matrix is defined, I mean, it can be decomposed properly in eigenvectors, these lambda alphas, and they are the so-called entanglement spectrum, and eigenvalues and eigenvectors phi alpha. Okay? You can easily obtain typical entanglement entropy, which is the measure of entanglement for pure states. This is taken by minus trace of log of rho, and you, I mean, sometimes are interested in entanglement spectrum, which immediately gives the entropy. Okay? Let me give you a few examples, concrete examples, why this is interesting at the many-body level. Okay? The first one is about dynamics. This is actually experimental reality. How thermalization does work in conventional quantum system. Well, this can be tracked by measuring Rayleigh entropies as a function of time, and this has been done already in the group of Marcus Grein, and in particular what he sees is that this interesting increase, this is the Rayleigh entropy as a function of time, and what he sees at very short time is a linear growth of the entropy, which is very typical of systems that want to thermalize. Okay? Now, another example is actually in the context of topological order. This is so far, I would say, restricted to theory, and the idea is that has been put forward by Lee and Haldane is that beyond entropy, you can get much more information by looking at the eigenvalues of the reduced density matrix. This is the so-called entanglement spectrum. And what Lee and Haldane showed, I mean, this is a numerical experiment performed here, is of the entanglement spectrum as a function of essentially of system size, by partition size, is that what you typically observe are features in the entanglement spectrum, like finite entanglement gap and a certain dispersion relation, that mimic exactly what happens at the edges of a topological state. So even if I take a fractional quantum mole, I put it on the torus, there is no edge. If I look at its entanglement properties, I can actually read off the edge information essentially exactly. Okay? So this is this Lee and Haldane conjecture. So I can use it as a diagnosis. as a diagnostic. So the third example, I think many of you have seen this in different contexts, is characterizing quantum complexity. And typically, I mean, if I give you a certain many-body problem, unless you're able to solve it at the wave function level, for instance, by an exact solution, it is extremely hard to get this spectrum, this lambda alpha, because then you need to do SVD. I mean, if you have, for instance, Monte Carlo method, you have no idea how to do that. Okay? So this is somehow telling us that for generic systems, these lambda alphas, how many eigenvalues I have, they are characterizing quantum complexity. And if you're interested in tensor networks, you for sure know that this is essentially what limits DMRG methods when one is dealing with more systems which are more than one-dimensional. Okay? Now, how to measure entanglement in experiments? I've given you a very quick overview before. I mean, typically the reaction of an experimenter when I say, okay, well, that is what the hell are you saying? Okay, stop. Well, indeed, it is something which is fundamentally complicated. It's not something that we can immediately relate to the things that we are used to measure, like correlation function or spectral properties. Okay? So that's justify it. I mean, so because I was mentioning tomography. I mean, you essentially forget about it in many-body system. Okay? It's beyond few spins, it's essentially impossible to do that. We have copies. Okay, this is very interesting. It has been pushed to a relatively large system, but this still requires exponential scaling, and in some cases it requires actually physical copies to be realized, which is not feasible or practical. Okay? And the full entanglement spectrum is even harder because you also require some Sillas and so on and so forth. So our idea, well, okay, this is just a very sketchy thing about this real copies instead of, virtual copies instead of real copies, and this is what has been done in Randall-Bratt group. But I will suggest that if you're interested in this, we just go on and discuss later on. Okay, so our approach is actually not focusing on the density matrix, because it's a very complicated object. We don't know how to probe it, but is to focus instead on what is called entanglement Hamiltonian. Okay? The first motivation for doing this is just psychological, because if you tell me how do you understand density matrix, I have to confess I have no idea. But if you give me a Hamiltonian, well, I know a few things. Okay? So we know how to handle that. So what are these entanglement Hamiltonians? They are essentially this object. Okay? You can write down whatever density matrix I give you as an exponential of some operator. And this immediately puts us in the field of statistical mechanics, because this is nothing but a partition function. Okay? Now, if we want to probe features of a partition function, we know how to do it. If we want to probe its spectrum, spectroscopy, one of the most developed tools in hemophysics. If we want to probe, for instance, entropy, specific heat, or heat capacity. We know how to measure these things, well, either in numerical or in real experiments. Okay? So that's the reason why the interest is actually shifted from rho A to these objects. Now, for historical reasons, sometimes people call this object not entanglement Hamiltonian, but modular Hamiltonian, and I will tell you why in a minute. Okay? So this is really kind of the most important slide. Do not focus on rho, but focus on this H tilde, entanglement Hamiltonian. So, well, okay, maybe this is just a reformulation. You tell me, okay, yeah, you have not simplified the problem at all, because you're just mapping one object into the other. There's even a logarithm of an operator, which we don't like to take. And what does it mean? Okay? Well, how can we get this entanglement Hamiltonian? Well, the first thing that you see as a reaction from a quantum information theorist, and this is actually a very reasonable reaction, is that this is typically highly non-local operator. Okay? So you don't want to deal with that. It's not necessarily nearest neighbor or next nearest neighbor. It can be arbitrary. Okay? And not only arbitrary, this can contain arbitrary many-body interactions, like 5, 6, 7 body. So it's completely unrealistic. Okay? Not only this, but typically, how do you get it? Imagine that I give you an Ising model, and I'm interested in an experiment that performs entanglement measures of an Ising model. What is the entanglement Hamiltonian? Okay? Well, the reality is that this problem was actually solved in 1975, and then essentially forgotten. Okay? Was solved in a field which is called axiomatic quantum field theory. And let me say, 1975, this is essentially, okay, I don't even know if people use extensively reduced density matrices at that time. Okay? So let me briefly discuss this theorem, which goes under the name of Bisogniano-Wickman theorem. Okay? It's essentially a theorem that tells you how you get these objects. Okay? For our purpose, we only need one thing, is a Hamiltonian h of x. If we had, I don't know, a near spin chain, this would just be nearest neighbor interaction, and maybe a local magnetic field. Okay? Now, forget about this must be Lorentz invariant, blah, blah, because this is obviously something which is related to field theory. I will be discussing later something which is at the lattice level. Well, the idea is that these people, these two guys, actually show that if you have a model system of this type, the entanglement Hamiltonian, given an half partition of the system, so you cut it into half, is just given by this formula, which is the following. This is an integral over x of dx. If you just add h of x, this would be the original Hamiltonian, which is nothing but the integration of the Hamiltonian density, okay, over the full space. Well, here there is one object more, which is this x. Okay? So this is telling us the following, is that the entanglement Hamiltonian is nothing but the original Hamiltonian, but the couplings, they depend on the position with respect to the boundary. Here x denotes the distance from the boundary. Close to the boundary, the couplings will be very small, because this x is close to 0. Far from the boundary, they will be very large. Now, you can interpret it as a physical quantity, or you can interpret it as what people call entanglement temperature. This is one way, actually, of understanding the Uru effect, which was first understood with Bisogniano-Wickman theorem. So if I, instead of writing x, I write a beta of x, an inverse temperature, this is telling me that the entanglement Hamiltonian sees a very hot temperature close to the edge, which, okay, it's reasonable. The edge is the part of the system which is mostly entangled with the other part. And instead sees a very cold temperature far from the edge. Again, rather obvious, because far from the edge, there is essentially little entanglement left with the B partition. Okay? So, in terms of thinking about it with experimental application, there are two messages that this theorem tells us. First, the entanglement Hamiltonian of relatively interesting many-body system is local, okay? Has the same structure as the many-body system itself. The only price to pay is this has to have couplings which depends on position, okay? In a very smooth way, x. We don't have to have arbitrary single-set addressing to do that. We just have to have, like, linear gradients and things of this type. So this is telling us that if we have, like, light-mediated interactions, which depend on Rabi frequencies and typical things, this is something which is conceivable, at least. Okay? Now, this theorem, just as an historical note, is very well known in the context of high energy. People use it. In quantum information condensed matter, you will see very little reference to that. It's a kind of a hidden paper, and hidden for some reason, because it's essentially unreadable. Maybe this is should not be recorded, yeah? But it's very, somehow, tough language. Yeah? Now, if you want to measure the entanglement spectrum in the experiments, in view of this result, this looks relatively simple. I mean, in principle, you have to find entanglement Hamiltonian corresponding to the problem that you're interested in. You have to devise a protocol to realize it. And then you just have to do spectroscopy. Because by measuring the eigenvalues of this operator spectroscopically, you have immediate access to the eigenvalues of a given reduced density matrix. Okay? The real issue is this theorem, I mean, is a field theory result, as was mentioned before. I mean, does it really hold when we are dealing with the typical models that we are interested in AMO physics, which are typically lattice models, okay? And in order to do that, we did a lot of extensive studies, and I have to say, we are not the only ones. There are also related papers, very recent ones on this problem. And let me just give you an overview of some of the results without going into much details, okay? So the first thing we do, I mean, the first time I've seen this result, I said I did not believe it. Yeah, it's obviously that this cannot be true. So let me code it. And okay, what you have to do is very simple. You have first a system here, which is the easy model. You take a bipartition, and here the couplings are constant. And then you take another model, which is again the easy model. But instead of having the couplings homogeneous, you take half of the system, and the couplings are just n times j. So this coupling is 1, 2, 3, 4, 5, and so on and so forth. This is the entanglement. You compute the entanglement spectrum of this guy, and you compute instead the physical spectrum of this guy. And then you go and compare. What you find is this. This is a system of 20 sides. And you see, I mean, these are ratios of gaps because you want to clean up non-important features. And they essentially lie on the top of each other as a function of delta, which is the strength of the magnetic field, is lambda here, sorry. So, and what was surprising is that this is also a very small system. I mean, why the hell should the result work so well for the easy model? We didn't know. And actually then we realized that for the easy model, this result is actually exact even at the lattice level. This was proven in an old paper by a Japanese group in the 80s and then rediscovered by Pescher and Eisler. Okay? So that's good, but there is a problem. That for easy model, even mean field works. Okay? So this is the worst test you can think of. Okay? It's not good enough. So we say, let us try to do something a bit more complicated. Yeah? And what we did, we tried it with conformal field theories on the lattice. This is just free fermions. This is a spin chain. And the dots here are the Bisogno-Wickman entanglement spectra, and the lines are DMRG computed entanglement spectra of a given model, of the model. And they essentially lie on the top of each other at the 10 to the minus 8 level, depending on the system size. So this was also working. However, I mean, critical systems, they might be somehow very lucky. We don't know, let us try to do it in another system, and then we say, okay, let us try a topological phase, which was already mentioned yesterday, is the Haldane phase. And in the Haldane phase, what is important is that this entanglement spectra, they must show topological degeneracies, okay? Now, what I will show you now is just a list of numbers, which is not very beautiful, okay? These are the Bisogno-Wickman, these are the Bisogno-Wickman results, and this is instead the original entanglement spectrum. You see that they have degeneracies. And what is important is that the degeneracy is essentially exact, okay, on one side of the other and the other. The values are different because they should not be the same. I'm plotting slightly different things. But the message is that at the level of 10 to the minus 7 or 10 to the minus 8, depending on the specific parameters of the model, this Bisogno-Wickman is able to predict the exact properties of this entanglement spectra. Okay? Sorry, this slide is ugly, but I mean, it's the only way I can really see a degeneracy properly by just plugging in all the digits. Okay? Now, I hope I convinced you, I tried to convince you that Bisogno-Wickman is a very strong result at the theoretical level that allows us to understand the structure of entanglement. Now we want to make use of it. Okay? Well, the first thing, we can do spectroscopy, as we were mentioning. So the idea is that we have to engineer these Hamiltonians, which have spatially dependent coupling, and then we just have to do spectroscopic measurements. This can be done in many different settings. From the cold atom viewpoint, the easier is probably something where you can have overall shape of interaction, which is Rydberg systems. Why so? Because in Rydberg systems, the strength of interaction can be tuned through Rabi frequencies. And Rabi frequency is something that is possible to modulate spatially. Okay? And this is one of the examples that we discussed. It's actually relatively simple, okay? In a scheme which has been pioneered by work done with Alex and with Rick and Thomas, which I think are somewhere in the audience. Okay? And the idea is here that by changing this Rabi frequency locally, you can have these linear shapes or inverse parabola. This is also another option that we can use, and so on and so forth. And these are results of spectroscopic measurements of this entanglement Hamiltonian by means of numerical simulation, accounting ground state preparation, noise in the measurements, blah, blah. Okay? These are without noise, you see, as a function of, this is the entanglement gap, as a function of delta, the magnetic field. This shows the phase transition, which is the easy phase transition. And this is instead the results, including noise, including finite time in adiabatic state preparation, and so on and so forth. And you see that the typical thing that you are seeing in this plot is that the only effect of the imperfection is to blur a bit the main result, and this is natural because it's a typical thing that you have also in spectroscopy. So in terms of errors, measuring entanglement spectra is the same. Is the same thing as measuring conventional spectra, okay? And has the same resilience to imperfections. Now, I don't know how much time I have left. Okay, so 6. Okay. So this is about entanglement spectra. This can be a rather, is to start with a rather abstract concept. So can we do something at the level of entropies? Okay. The idea is, we have been discussing these eigenvalues. We want to discuss something which is a collective effect of all the eigenvalues, like the von Neumann entropy. Is it possible at all? Well, what I want to show you, these are ideas which have been pioneered by these guys, Tiago, and which is actually from not very far from here, and Giuliano. The idea is very simple, okay? So let's suppose that you're interested in the von Neumann entropy. Well, the von Neumann entropy is nothing but the expectation value of the entanglement Hamiltonian. Okay? I can write this is e to the minus beta h, or e to the minus h tilde if it would be equal to 0. So this trace of e to the minus beta h log of e to the minus h, well, take the log, expectation value of the entanglement Hamiltonian. This sounds very interesting, because as I've shown you, this entanglement Hamiltonian is made out of local pieces. So this implies that there is a chance of measuring the von Neumann entropy by means of completely local measurements. Okay? The trick here is obviously that you have to take into account the spatial dependence. Okay? So this looks completely trivial. There is actually one thing which is important, is that when you do that, obviously in terms of implication, this is in principle very powerful, both for experiments theory and also numerics. But there is one catch, is that when I wrote this, one should not forget that these entanglement Hamiltonians have a problem of normalization that I did not discuss. So one has also to consider there is a log of this type. This is a constant, but might be important to determine thermodynamic properties. Okay, so what one has to measure in experiments is actually the full entanglement Hamiltonian, and this implies doing a thermodynamic experiment like a specific heat. Okay, you integrate a specific heat, you get the von Neumann entropy like a conventional thermal entropy. This can be done in two things, either in numerical experiments, and I think this is important if some of you is interested in Monte Carlo. Monte Carlo is known to have problems in calculating entanglement, okay? The only thing it can be done is to calculate Rayleigh entropies, which are not entanglement measures, as something interesting, but the von Neumann entropy, nobody knows how to calculate. Well, this way is essentially telling us you can calculate entanglement entropies the same way you do as thermal entropies in classical Monte Carlo. It's a method which is called Wang-Landau. And the second, in experiments, you can imagine that if you realize this entanglement Hamiltonian, you can perform a thermodynamic measurement of a specific heat, you integrate it, you get the von Neumann entropy. Okay? And let me give you just two quick examples on this. This is about measuring what is called central charge in quantum critical systems in one dimension. In one dimension, the entanglement entropy under certain condition of a ground state cannot scale with the size of the system, but it scales with the logarithm of the size of the system, of the subsystem, times a prefactor in front. This is called central charge. And these are somehow simulations where this is the exact result, the blue line, and these are instead the entanglement Hamiltonians results through, for instance, measuring the specific heat, and they essentially lie on the top of each other. Okay? And these are two examples on a spin chain and an easy model. Okay? So for measuring the central charge, this is good, but what I find even more amazing is that one can study systems where it's essentially very hard to make directly predictions at all. And this is the example of two-dimensional quantum magnets. In two-dimensional quantum magnets, there has been a prediction that the entanglement entropy of a subsystem scales like the perimeter of the partition between the two, this dA. This is typically a non-universal factor in front. And then there is a correction which goes with the logarithm of the size of the system. This is very important because this coefficient B tells us exactly the number of Goldstone modes in the system, okay? Something which is not immediately trivial how to calculate otherwise. And these are few examples on the both XY and Heisenberg model of, here we cannot compare with exact results because it's impossible to calculate it. So it's impossible to do a tensor network simulation which is reliable and measure this. And so we have to rely entirely on our method, and we measure these quantities and they are exactly matching within less than 1% the expected value from this prediction. And this can also be something which is measurable in experiment through a specific heat. Now, there is a problem that, we are now witnessing a lot of experiments where actually there is no reservoir at all, okay? So in a system where there is no coupling to any reservoir, I have no idea how to measure a specific heat, or at least it's not immediately clear. But what can be measured is heat capacity, okay? Heat capacity in the entanglement concept, this is entanglement capacity. And this is nothing but the variance of this object. Okay? So in principle, there is another way, by exploiting this Bismuth-Wickman theorem, to measure that in experiment. This is an example taken from a model which has been realized recently in these experiments over Harvard. It's a spin model in one dimension, where there is a constraint on nearest neighbor, so the two atoms cannot be excited at the same time through blockade. And then there are local terms, like a Rabi flop, local chemical potential, and additional neighbor interactions. This model is actually very interesting for a series of reasons, and what is important, it hosts transition lines and transition points which are very exotic. And some of them are conformal, so what we did, we said, okay, if you just measure two-body correlation functions through this entanglement capacity, can you actually predict the central charge of this model by measuring it in experiment? And these are the numerical results that show how this is possible. I mean, the result that we get for the system size that have been done so far in experiments is actually within 5%, within 10% of the exact value due to limited system size, and is working quite well. It's not working very well in a particular part of the phase diagram, which is a Potts critical point. And if you're interested in why it does not work very well, please come and ask, because this is related to the entanglement structure of constraint system, which is very non-trivial. Good. I think I'm done. Conclusions. So the story I want to tell you is that entanglement Hamiltonians are a new way to look at entanglement properties with respect to experiments. They are not a new concept, because this has been around in high energy for a long of time, but it is that they can provide a new link to experiments, which we find interesting at two levels, both measuring entanglement spectra and maybe entropies or entanglement capacity. And what I want to emphasize is this is done by conventional tools, okay? So we don't have to reinvent the wheel. It's just spectroscopy, measure of correlations, and thermodynamic measurements. And is adaptable to many platforms where there are light-mediated interactions. So with that, let me thank again my collaborators, Benoit, Peter, Giuliano, and Tiago, especially Benoit, Giuliano, Tiago. These are the guys that did most of the work. These are the reference, and I thank you for your attention. If you're happy, I'm happy to discuss over caipirinhas. Okay.
Thank you very much. So, questions?
Can you comment, Marcello, on the importance of Lorentz invariance for the proof of the theorem, and if there is a sort of non-relativistic analog for that?